Record somehow. Why can't I record? All right. Good morning, everyone. So I had a few updates before we get started. The first one is, oh, here it is. Course schedule. So let's see. We've got our draft report is due this Saturday. Next week, we've got a guest speaker, our final guest speaker. And then I was planning on asking people to give peer feedback on the draft reports. So because just like with the talks, giving feedback on a report gives you a chance to think about how you could improve your own, and it's also really useful. But I wanted to ask you all, do you think it would make more sense to get peer feedback on the draft report or peer feedback on the final report? The final report will be more polished. Getting feedback on the draft report would probably be more useful. And if the final report isn't due until December 12th, I feel really bad asking you to, quickly read a couple reports on like December 14. So I'd really ask for your advice. What do you think would be better for you? Draft. Awesome. Okay, it looks like we have a consensus. Okay, so we'll stick with the draft report. And I had a whole list of things I wanted to, oh, here it is. Okay. Also, we had talked about, I'd originally planned on having 4 exercises, saying you need to do at least 2. I've been having trouble coming up with a really good 4th exercise. And I'm really against making work for the sake of work. So if you have not done 2 exercises yet, or you would really like another exercise because you didn't do well on the first one, please reach out to me and we'll come up with something. So, because I want it to be useful for you. If it's not useful, then there's no point in doing it. So please, if you're in that situation, please reach out to me directly and we'll figure something out. Also, I realize normally when I teach, I give mid-semester evaluations like, hey, how's the class going? What do you think we should cover? And I was thinking, yeah, I should probably do, it is way past the middle of the semester. I mean, I've got the schedule right in front of me, but it still feels like, early October to me. And I realize we now have less than 3 weeks left, and that's just crazy. So I apologize for that. But that means when we do the final evaluations for the class, I will ask you to really spend some time thinking about what I could have done differently, what you liked, what you didn't like, because I do plan on teaching this class again, and knowing how to improve it is personally really important to me. So I don't know how evaluations work at U of A. I'm still trying to figure that out. Actually, have any of you do you have access to evaluations for this course yet? No. Okay.
No, evaluations are typically done, I think, like the last-ish week of classes.
Okay, because I found a website saying, a U of A website saying that students can access the evaluations anytime after the withdrawal period before classes end. And that just seems wrong. Anyway, I'll figure out.
Normally send out emails for what are they, USRIs, whatever they're called. And so if they're open and available anywhere, I haven't received an email for it.
Yeah, okay. we missed the midterm evaluations, Matt. I think we needed to request it from USRI.
Oh, yeah, I actually just do an informal one. I don't need a official. So anyway, when those emails come out, I'll probably remind you to take those evaluations, because I really would like to get your feedback, and that's a good way of doing it anonymously. Let's see. Also, I logged into Discord today and saw that one of the people changed their had a problem and had to change their schedule. So we only have 2 presentations today, and I was caught off guard. I should have produced some content, but I couldn't throw anything useful together. So this will probably be a shorter class than normal. I apologize for that. The final thing is I am planning on the last week of classes that on the December 1st and 3rd that will get the chance to do presentations, because again, I think presenting is important, getting peer feedback is important, and you guys are doing some awesome stuff. So I think it will be really good to again show how many cool things that's happening. But I was also wanted to know if any of you had thoughts on alternatives. So I was planning on just saying, okay, we've got this many groups, we've got this much time in the 2 classes, so we just have, you'll have 18 minutes or whatever it is. But I was thinking we could do something more creative. So if you didn't want to do a live presentation, what if you did a 10-minute video and then did live Q&A? Or what if you did a 15-minute video, gathered all the questions, and then another 5-minute video? So, I mean, since everything's remote, this kind of stuff is relatively easy to do. It's not that much harder than just giving a presentation on Zoom anyway. But I was wondering if anyone had any suggestions or preferences. Are you doing anything fun in your other grad classes, or is it just business as usual?
So I was just thinking, I think doing like some sort of video or something maybe beforehand and then doing the QA is not a bad idea, because otherwise we might be kind of crammed with time for 2 days. And usually the exciting stuff is asking the questions to people after.
Well, and the other thing I was thinking of is if we had some of those videos and you were okay with it, I would love to use those kinds of things to advertise the next round of this class. Because you guys are doing awesome stuff. 2 years from now, if students are saying, well, how would I spend my time in Matt's class? And I'm like, look, there are all these cool examples. What do other people think?
So something that I kind of missed about being in class in person, this is my first semester here, is like chatting with other people about all of their projects and like seeing how you can connect that to your research. And I feel like it'd be, I don't know how to structure that, but it'd be really nice to talk to the people in this class for that.
Yeah, well, one thing that a colleague suggested, which I didn't do, was, it's so hard to be social these days. If you can bake some time into your classes for social activities, or have like, at a happy hour or something like that. I thought that was kind of a cool idea, but sounded like too much work. But if we did this video, then maybe the Q&A would also be a chance to develop these kind of connections on the fly, or at least figure out who you want to connect with and chat with more after this class is over. Ooh, yeah, Revan, what do you mean?
Yeah, like instead of like a formal presentation, I don't know, we have 2 days, so half of the people could kind of prepare like a virtual poster kind of thing. And then using breakout rooms, people could, mingle about and then talk to those groups. And then the next day, the other half would present their posters or whatever. And then that way, you get to present your work, but you also get to chat with people.
Yeah, I like that. So the way some conferences have been doing it is you record your 5-minute or your 10-minute talk, and then you can hop into individual rooms and chat with people. So one thing we could do to modify that slightly would be have people record a video, but then plan on having these individual or having the class split up into basically Q&A time, but they could also have this kind of poster format where, just like one slide reminding people what their talk was about. So there's something that they could point at easily. Yeah. So the 2-minute talk with a virtual poster presentation. The thing, I like the breakout room idea. One potential problem is that everyone goes to poster one, gets stuck there, and none of the other posters get to see anyone. I mean, I guess
you could just force everybody to leave like you did on those other breakout rooms sometimes, you know, that countdown.
Yeah, that's true. But then, so I guess the difference then would be the Q&A is a much smaller, more intimate group rather than being the entire class. So that's one benefit. One con, though, is that if you're in poster group 1, you don't get to see any of poster group 1 posters, right? If you're presenting, then you don't get to see any others.
I think in Zoom, you can also just go to whatever breakout room you want to as well. Like there's an option to do that from what I remember.
Yeah, there is. You can set it up so that participants can choose which breakout room to go to if you've updated the latest version, which of course changes daily. Okay. So this gives me some ideas. Let me think about it a little more, and then I'll probably post a poll on Discord and ask you guys what makes the most sense to you, and we'll hopefully come up with something fun like this, just to make it a little bit different. But worst case, we can always go back to the tried and true presentation Q&A, and yeah, not my first choice, but it is always a backup. Okay, so any other comments or thoughts or questions before we get started with our 2 paper presentations today? Okay, I'm going to take that as no. So let's see, who would like, remember we're going to, you're welcome to drop questions in the paper presentations Q&A, but also if you take a few notes while during the presentation, then you can drop those notes, at least one thing that you liked, at least one thing that could be improved or different, and it could be either about the presentation itself or the work they're talking about. So who'd like to go first?
I guess along with Malika and Varshini, I go first.
Great.
And let me just share my screen. Yeah. Okay, I hope you guys can see my screen.
Yep.
Yeah, perfect. How do I take this off? Yeah. Okay. So today the paper that we chose was is titled From Theories to Queries, Active Learning in Practice. It's by Burr Settles. And the reason why we chose this is because we are trying to implement something that would kind of combat the drawbacks of active learning, particularly one drawback about which I'll be talking more. And all right, so let's start off. So this paper provides an in-depth view of active learning along with the drawbacks. And as we know, Matt told us that active learning is a special case of ML in which the algo can interactively query with the oracle. The oracle might be an expert human, or it might be another computer system itself. And the advantages associated with active learning are that it is more economical, because in supervised learning, you would need perfectly labeled data points, and you would need a lot of them. And active learning kind of is more economical. It needs a reduced training set, and it also provides higher accuracy. But there are a lot of disadvantages associated with it, and one of the major disadvantage is noisy oracles. So we always assume that the oracle is always perfect, like, it always tells us the right things, kind of like a mons. We assume that it always is right, and But the problem is that sometimes there might be noisy labels as well. I will be talking more about that. So let's focus on the first problem is the querying in batches problem. So usually in active learning, the learning algorithm queries the oracle and it is only done for a single data point. Um, but the problem is that it is very expensive. So every time it queries the oracle, gets the label for the data point, adds it to the training set, and trains again and again. And for larger problems, this might be very, very expensive and it is slow. And one of the solutions for that was to query in batches. And the problem with querying in batches is it should know which data points to group together. And sometimes the group together data points, they might be identical in nature. So that is a waste of time. You're basically querying the same kind of data points over and over again. So that is one of the problems. So the methods used to solve them in previous papers where you could kind of, oh yeah, let me just take a look at my notes. So the QBest, there was this algorithm called the QBest algorithm. It was a naive approach where all the potential query instances, they were grouped together and the best of them were selected according to some utility measure. And like I told you, it is kind of problematic because identical queries may occur. And some of the approaches to battle this were you could probably do a clustering algorithm where you cluster similar queries together and take only the centroids of those queries. And there were Bayesian reduction techniques used, and they haven't explained a lot more about this. And the third could be to use gradient methods to identify the best query. And okay, over to noisy oracles. So this is where our main focus is. And like I told you, the expert labels might not always be, done by an expert. So some of the instances to be queried, they might be difficult for people as well, because they might be ambiguous in nature. People can become distracted or fatigued over time, and they might not be able to give the best judgment on those data points. So the methods to solve them were to use crowdsourcing tools such as Amazon's Mechanical Turk and online games to label the data points. And you could also use the expertise of multiple experts as opposed to non-experts. And one way, so one of the papers, they talk about using agnostic active learning, where the oracle isn't always assumed to give the right labels. And the third approach was the learner may repeat queries to be labeled by multiple annotators. However, the problem associated with this particular point is that the learning algorithm should know when to query once. The learning algorithm should know when to query multiple times for the same query, and things like that. Over to, okay, no. So annotation is a noisy process, and some of the papers, they assumed that all the annotators were equally and consistently noisy. And here comes the interesting question. So how do you think payment may influence the annotation quality? For example, if you pay the non-expert twice as much, are they kind of forced or motivated to be more accurate? This kind of is integrated in ethics as well. Just because you pay someone more, does it mean that they are more, they work harder? Something like that. And over to, yeah, so do you guys have any thoughts on this? How might the effect of payment influence annotation quality? Let me just look at my Discord. No. Okay, no.
So one thing you could do is make their payment based on their accuracy. So you give them bonuses if they give you better labels. But that means you would have to be purposefully asking them to label things that you already know the answer to.
Yes. Yes, but again, I have another question for you. So do you think especially medical, in the medical domain, do you think an expert annotator, even if you pay him or her more, would they do a better job than oh sorry, if you pay a non expert annotator more, would they do a better job than the expert annotator? Especially in the medical domain. Imagine you're looking at CT scans of probably the lungs to determine if the person in question has lung cancer or not. It would be helpful to incorporate the use of a expert annotator rather than a non-expert annotator, right?
So the idea is that with the right incentives, you might be able to get a non-expert to increase their label quality.
Yep.
Huh.
One of the ideas.
Cool.
Yeah. So over to Varshini, she will be talking about the rest of the problems, and then Melika would talk about what our approach to this problem of noisy oracles is.
So, am I audible?
Sorry, I just had a quick question. Could I?
Yeah, sure.
Sure.
I was just wondering, like, even if you pay a non-expert, like, a ridiculous amount for their annotation in order to kind of like motivate them to improve their accuracy, I don't know if they'll ever kind of reach the same level as an expert on the same task.
Yeah. Again, it makes sense, but it depends on the domain, I guess. For a medical domain, you certainly cannot. An expert annotator would always be the best. But if it's somewhat a generic domain, then maybe a non-expert, it need not be a lot of money, but if you pay them higher amount of money than what they would usually get, maybe it might influence the annotation quality.
Do you buy that argument, Laura?
I'm still a little skeptical because I feel like there's always going to be some upper bound on what can be expected from non-expert annotators. But
Well, let's take the extreme example. Let's say you've got this doctor who's treating a ton of COVID patients, and you've got this annoying professor who's asking him, hey, can you label this CT scan for me? Versus you go and get 100 people who are not experts, but they agree to spend a lot of time looking really closely. I mean, I bet you could come up with some scenario where you might be able to find a trade-off, but it does probably depend on the difference in between the expert and the novice.
and the difficulty of the task.
Yeah.
Yeah.
Yeah, like painstaking pixel-wise annotation of CT scans might end up being done better by non-experts because the expert would be like, this isn't even worth my time, and might just flick through things.
Yeah, you are not paying me enough for this garbage.
Yeah, that's a good point.
Yeah, so over to Varshini, and yeah.
So, am I audible?
Oh, yeah, you are.
Okay, thank you. So, I'll be talking about multitask active learning. Active learning settings typically assume that only one learner is solving a single task. Although this is not the case in many real world problems, the same data instances may be labeled in different ways for different kind of subtasks, right? So in those kind of cases, multitask active learning would be more economical. It basically tries to label a single instance for all the subtasks simultaneously. So that's essentially what it tries to do. So to give an idea of a scenario where multitask active learning would be useful, consider this, a database of film reviews. So what could you do with this? We could potentially extract the names of a crew, classify the film type, or estimate a rating based on the textual review, right? So there are a lot of things you can do with this. So, but if you are trying to solve each thing separately, typically you would, employ 3 different, independent learners. Say, for instance, in this case, a classifier to classify the film type, and an entity recognition to kind of extract the names of the crew, and then a regression model or something like that. So what the main challenge here is, how can you effectively select queries that will benefit all three learners instead of, selecting queries for just one particular subtask? So do you guys have any thoughts? Don't move to the next slide yet.
Yeah.
So yeah, I think you can go to the next slide now. Okay, so these are some possible solutions that have been studied for a two-task active learning scenario. So they studied a system where, just a second. So they studied a system where they had a natural language parsing task and a named entity recognition system. So what they tried to do, a first solution that they proposed was alternating selection. So basically in the first iteration, you allow the parser to query sentences, and in the next you allow the entity recognition system to query sentences. So that's one thing you could do. And the second thing is a rank combination. So basically you query the data points and you give a rank based on the importance of data points in both the tasks, and you kind of give a combined rank. So that way you might get a combined rank for both the different tasks, right? So you know how important one task is. An instance is, sorry. Yeah, the next slide. So another problem that's often you face in the active learning in real world is, so you don't often know the model or feature set initially, and also you're probably uncertain about which model you're using. So but this is usually not an issue. Most work in active learning has assumed that the appropriate model class for the task is already known. So it's safe to use active learning in such cases. But what happens when we don't? A random sampling may be more advisable than taking one's chances on active learning with the wrong learning algorithm, right? So that would be a big mistake. So this brings up a very important point for active learning in practice. So change of model or uncertainty about the model can potentially become problematic. So there have been instances where the change of model has actually benefited the system. So they tried to use a training data that was classified by a decision tree classifier on an active naive based learner, so that actually helped the system. But there have been cases where they tried to do this and they failed. So they suggest that the best alternative in such cases, when you're not so certain about the model initially, is to use a heterogeneous ensemble to select the queries. Yeah, over to Melika.
So the last problem could be a variable labeling cost, which is could be different. So the goal in the active learning is minimize the overall cost of training an accurate model. Then simply reducing the number of labeling instances doesn't necessarily guarantee a reduction in overall labeling cost. So it could be one approach that reducing annotations effort is in active learning involves using the current trained model to assist in the annotation of queries by pre-labeling them in structured learning tasks like parsing or information extraction. But such methods don't actually represent or reason about labeling costs. So by minimizing the number of annotation actions that requires for query that has already been selected, we have to reduce costs indirectly. So there are two approaches. The first, non-labeling costs and for cost-sensitive active learning approach, it is varying labeling cost while selecting queries. So in Cooper et al., they said that decision theoretic approach could be worked by takes into account both labeling costs and misclassification costs. So in this setting, each candidate, for example, query is evaluated by summing its labeling costs with the future misclassification costs that are expected to be incurred if the instance were added to the training set. And for example, they make this reasonable assumption that cost of labeling and instances in a linear function. For example, they could put 0.01 per second for voicemail messages, or for each error that will be that they would be labeling, they have to pay, for example, $10 for per error for misclassification costs or something like that. And for unknown labeling cost, the cost of annotating an instance is still assumed to be fixed and known to the linear before querying. So a novel approach to this cost-sensitive active learning is setting where annotations costs are variable and not known. For example, if cost is a function of annotation time, and we don't know in advance how long the annotator or experiment will take. So this could be really hard to think about it. And in this approach, one can learn a regression cost model and which tries to predict the real and unknown annotation cost based on a few sample meta features on the instances. Or other problems could arise that annotation costs are not approximately constant across instances. So they would be vary in some domains. And also the cost of annotating an instance may not be intrinsic, but may instead vary based on the person doing the annotation. And the other problem that could be affect the measured cost for an annotation may include some components. For example, in practical, there are two types of noise which affect annotation speed, which is jitter, a minor variation due to the annotator fatigue or latency, or maybe their pause. This is major variations due to interruptions that should be shorter under normal circumstances. So to wrap it, all these things, we just think about how can we reduce the noises or some problems that we could face in our project. Then we just found that RANSAC, which is a random sample consensus, could be help to reduce noises that we have in our project. So a random sample consensus, or RANSAC, is according to Fisher and Bolus, the philosophy of RANSAC is opposite to that of conventional smoothing techniques. Rather than using as much of the data as possible to obtain an initial solution and then attempting to eliminate the invalid data points, RANSAC uses as small an initial data set as feasible and enlarges this set with consistent data when possible. So as you see in this picture, for example, a ransack will, for removing outliers, this algorithm starts with reading extracted plain points by the ransack algorithm and use some points randomly. And clustering start with the randomly selected points, then it's search for neighbors of the randomly selected points. Then it's going to search points distances is less than the given threshold. So if they're not less than threshold, so then it's going to be another loop. They search another points, and then randomly selected points and start new clustering. So finding new random points which are neighbor to the data points. And these points which are randomly selected has a fitted line, which is really good and good fit of the data points. So then another thing is just search search again and again for points to find the distances less than the given threshold. So when the algorithm finds all the neighbor points, then add points as of neighbor points, and then finish the ransack algorithm if non-search points left. So when we just want to use this algorithm, we just drew a flow chart that shows how we are going to use this algorithm in our project. So if you see that in this picture, the start point could get 20% or 30% of the data points. Our data points could be 15,000, 14,000, and we just get 2,000 of them. So with K iteration on active learning, we can find the most ambiguous data points. Then we can take all of them, take 95% of all data with new added ones, which are randomly added. So why we just want to take 95% of this data? Because we don't want to lose the data at the end of this loop. So we want to add more and more data points to get higher accuracy. So when we just measured this, we just get 90%, or even we can just use 90%, 95% or 90% of the data points to train, and then just leave aside just 10 or 5% of the data, which are waste. So when we just train the data points, we can record the accuracy with m times iteration. So with as much as we can iterate the training set, we can get different accuracy. Then when we get the highest accuracy of those iteration, we can take the 95% of the data that gave the best accuracy and finish the this cycle. So as you see, the n is coming from number of loops, and k is number of active learning. It's active learning iteration in one loop, and m is number of number of times to run ransack. And for this method, we just wanted to compare with the simple active learning that we had before. So if we have 20 times iteration on active learning method, so we have to use it, for example, 20 times iteration here. But with the difference that K iteration active learning is, for example, 5 most ambiguous things that we find in each iteration. So we could have 4 iteration at all to get 5 times 4 equal to 20 iteration as we had in active learning iteration. So after that, we could compare ransack accuracy and then traditional active learning method accuracy to compare these accuracy with each other. And that's it.
Cool, thanks. So are there, I think we've got time. Yeah, we've got time for questions. Could you say how this relates or how, if does it relate to the project you're working on?
Doesn't relate? I didn't understand that.
The final project for the class is ransack.
yeah.
How? Yeah. Okay. So how is that relevant?
Okay. Sorry. So our project aims to kind of account for the noise in active learning and improve despite that. So our baselines are going to be 2 active learning methods. We are using the least confidence in uncertainty sampling. We are using least confidence and the entropy based methods, and we are kind of hypothesizing, I guess. We are kind of telling that using ransack, incorporating ransack with the active learning algorithm would kind of account for the noise and improve the results despite the noise present in the oracles. And yeah, so this is sorry. So this is not the picture of the flowchart that you're seeing right over here. This is not this is kind of related to our project. This is not the flowchart of the ransack algorithm. This is the flowchart of the ransack part in our own project.
Oh, okay. I missed that. Sorry about that.
Yeah.
And then if I remember right, you chose a pretty cool data set.
Yeah, so we are using the EEG data set. We chose the medical domain, and I'm not exactly sure whose EEG data set that is. But yeah, it contains 14,000. Oh yeah, so it is the EEG data set that determines the blink of the eyes. So 0, it's a binary classification kind of a thing. 0 means the eye is closed, and 1 means the eye is open, and based on a set of features. And we are using the EEG data set since the medical domain is kind of very finicky. We also have a second data set that is text data. I think it is the coronavirus tweets data set. We haven't worked on that yet. We are sticking to the EEG data set. In case the results are very finicky, we would switch over to the other data set.
Cool, thank you. Any other questions from the class? All right, then I'm going to drop my comments into the chat while Vlad and Rohan get set up. Thank you for that, Shruti, Malika, and Varshini. I'm sorry for butchering your names. It's easier to learn people's names when they're in person.
You got my name right.
All right. I guess it's our turn to present. All right, then let's hit the present button. Can you guys see this?
Yep, you're good.
Excellent, excellent. Okay. So the paper that we are presenting about is called Effective Reinforcement Learning for Mobile Robots. And it's by Smart and Kelbling. And this is from 2002, just for reference. Okay, so the agenda, or what we're going to cover in this talk, is going to be the motivation of this whole paper, the learning framework that they use, the experimental results they got, and then the conclusions and some interesting points and maybe why we decided to build on this paper. Okay, so this is the motivation of the whole paper, basically. If you're going to remember one thing, it's this. So that programming mobile robots can be a long time consuming process. This is what they keep claiming. in 2002, and and I'll explain a little more in the next slide, but this is the main motivation. Now, this is hard and they want to fix this problem somehow. Okay, so the problem is that back then, I guess, one of the hard things was that they would have to actually program each of the sensors individually on the robot, and that'll take a long time. And you have to know like what each sensor does, and you have to be precise with it. And there's a lot of nuances, and it doesn't sound easy. And it take people like weeks just to program one like individual action. So that sounds very unideal if you want a robot to do like different things or more complex tasks, right? And so they found out that reinforcement learning was a very appealing idea because you can provide like this high level goal, maybe just like get one reward for picking up this object and 0 everywhere else. It seems very appealing. You just tell one thing and then it learns on its own. So that's kind of their main idea. It's like, okay, we want to use reinforcement learning some way in order to help these robots learn things, so we don't have to program all their individual sensors and take like weeks to do this. Okay, so then they mention things about there's 2 different ways we could kind of approach this. We can present the robot with like a very sparse reward, which is they give an example of like, let's say we want a robot to like reach some end goal, like maybe like walk in some like hallway and get to the end of the hallway. So we'll give it like 1 for reaching the end goal, and then -1 for hitting any like the walls. So this is a pretty sparse reward because most of the time it's getting 0 reward unless it like hits a wall or gets to the end of the maze or the hallway. And then they present some other like idea of the more dense reward. And I think this is like very common in reinforcement learning if you've looked at it, but the idea that like you can provide a reward almost for every single action you take if you're a little more clever with this, in the sense that maybe you can provide the reward as being 1 over the distance to the goal. So as you get closer and closer, your reward gets larger and larger because your distance is smaller and smaller. Okay, so that's the idea. But once again, these dense rewards are kind of hard and there's a lot of human bias. And in more complex tasks, it becomes difficult to decide what your reward should be. And so they favor sparse rewards. And then they bring up the challenge that sparse rewards are great, but it takes a very long time for the agent to discover where the reward is and to actually learn from that. And so then they finally propose that we can use human demonstrations or human knowledge as a way to help this robot learn, and specifically by using human trajectories or demonstrations as experiences for the actual agent to learn and train on. Okay, so that's like the main motivation. We're going to use reinforcement learning with human demonstrations as a way to help it learn. Okay, so now I'm going to talk about the learning framework here. So they use Q-learning with value function approximation. They use something that's different from DQN because I guess that wasn't around back then, and it's a more like there's a few checks that are used to make sure that it's like within the distribution that it's seen before, so that it's not like doing something completely weird. But I'm not going to go over that. Key idea is that it's using Q-learning basically and a form of value function approximation. And they want to use good sample trajectories, which are like the human sample trajectories at the beginning, and then let the agent learn on its own. And therefore, this learning is going to be split into 2 phases. So I'm going to talk about these 2 diagrams on the right bottom corner now. So there's a phase 1 of learning and there's a phase 2 of learning. And if we for now, like if we just exclude this kind of middle section of the diagram, which is called the supplied control policy, and we just look at the rightmost diagram here, we can see that this is like what we're quite familiar with in reinforcement learning. At the bottom, this learning system would be our agent. And at the top, it's the environment. And so the agent takes actions and that affects the environment, and the environment gives its observations, or if it's, I guess, partially observable, or states, if you know the exact state, and a reward. So this is the common reinforcement learning framework that you're probably familiar with. And they present adding this new thing called a supply control policy. And this is basically going to be your human. And they propose that this could be really a human or any sort of expert that gives better actions than the agent would on its own. And so if we look at the phase 1 diagram here now, we can see that basically the supply control policy decides on the actions, and the agent will have no power over the action. So maybe I can read exactly what I wrote here for phase 1, and let's say the control policy is used as agent behavior. So it directly defines what the agent's behavior is, meaning its actions. For all of phase 1, the agent has no power over its actions. And the idea is to expose the agent to interesting parts of the state space. And so it is, you don't want the agent to really like copy exactly what or learn this directly. You just want to expose it to kind of the interesting part of the state space hopefully the parts that actually give you some sort of reward. So it learns that, okay, this is like somewhere I should go in phase 1. And then phase 2, you essentially leave the agent to act totally on its own. This is like standard Q learning now. And we can just exclude this middle supplied control policy. They mentioned that it could interact with the supplied control policy in theory, but they make no mention of actually using it. So essentially phase 2 is just regular Q learning. So that's the idea. We're going to use human demonstrations as experience for the agent to learn in phase 1, and then afterwards it's just standard Q learning. And these are like the main takeaways that they kind of mentioned why this would be useful or helpful. So demonstrations are specifically used to generate experiences. So we just want good experiences at the beginning because the agent really has no idea what it's doing if you just like randomly initialize it with Q values. And then in phase 2, the robot will hopefully be capable of finding these sparse rewards, and hopefully it'll be able to get to these states, and learning will not stall, and it won't be in this like long loop of never finding a reward as it usually would in a sparse reward setting. And finally, human input can be provided without programming the sensors and without really knowing much reinforcement learning. Like you can simply imagine having like some robot with like some joystick, and you can just show like control the robot with the joystick as a human, show it, for instance, where like how to exit some maze, and that would be like the human demonstration. So you really need no good knowledge of programming or reinforcement learning. And so now Ron will explain to you guys what experiments they did and what results they got.
Great, thanks Vlad. Yeah, so they ran 2 different experiments. The first one just being a simple corridor following task, and then the second one being obstacle avoidance. I'll go in depth into both of those in the next slides. In terms of the setup, the mobile robot uses a laser rangefinder to identify the walls and obstacles. The learning rate for both experiments was 0.2, and the discount factor was different. So for the corridor, it was 0.99. For the obstacle, it was 0.9. And then they evaluated. So they would every 5 training runs they would perform an evaluation, and that's what we'll be seeing on the slides. The other thing to note is that the action space. So there are kind of two possible actions. There's the translational velocity, and then there's the direction, like the rotation of the robot. They kept the translational velocity fixed for both experiments, so that the robot only chose kind of which direction to move in. Next slide. Right, so here's the setup for the corridor following task. So it's a 3-dimensional state space. The three dimensions are 1, basically the distance to the end of the corridor, 2, the distance from the left-hand wall as a fraction of the total corridor width, and then 3, the angle to the target point. And that's the state given to the robot. The reward is 10 if the reward area is reached, and 0 otherwise, hence a sparse reward. And the supplied control policy, if you recall from Vlad's learning framework slides, the bit in the middle here for this specific task, for the corridor following task, was just given to be kind of this equation here, where theta is the angle to the target point, and they controlled alpha. But that's not really too relevant. And then the evaluation metric they use is the number of steps taken to reach the goal state. Next slide. So here's a plot showing the number of steps it takes to reach the goal state. And you can see here the left-hand side of the plot is showing the performance of phase 1, and then the right-hand side is phase 2. Note the 2 horizontal lines. So you have optimal here, and you have best example. So optimal was basically, I'll go into that briefly on the next slide, because here so I mentioned before that they were using this theta supplied control policy, but for this example, they also used a joystick control policy too, and optimal was the best control. It was the best that one of the researchers could do on this corridor following task, whereas the best example from the supplied control policy, where it was a function of theta, because theta, for the evaluation, they basically just run 10 different evaluations where each of them has a different starting pose. And so the best example was just happened to be whatever the best performance of those 10 were. So you can see after 30 phase one training runs, the robot was sort of deemed competent enough to take over. So hence the vertical line here. And so basically now there's no human intervention. The robot is taking its own actions. And you can see after about 30, 35, it's the robot's performing as well as the best human robot. And so again, what we're seeing here is the results. So every 5 training runs, they disabled learning, and then they evaluated the performance by doing these 10 different poses and evaluating the performance. The other thing to note about these plots and the ones following is that there's a temporary decrease in performance just after the transition from phase 1 to phase 2. And the reason the authors give for this is because when the learning algorithm takes over, when the agent takes over, it begins to explore a little bit. And so it creates some new experiences that that phase 1 wouldn't have encountered. And so then there's a bit of suboptimal exploration before it kind of learns to settle back into what it saw before. And yeah.
Sorry, quick question.
Sure.
Did they actually measure that to see if the states visited in phase 2 were different than the states seen in phase 1, or is that just something they observed casually?
They didn't specify that they didn't include any results about a hard comparison between the two. It seemed like this was a qualitative sort of derivation.
Cool, thanks. Also, Laura had the question in Discord: are the steps equivalent to time?
No, each of these steps is an evaluation, or sorry, I should say, they'll run the they'll do each. So it's a training run. So it's I guess it's equivalent of episodes.
No, so what is the y-axis that says steps?
Oh yeah, that would be time.
Okay, cool.
Yeah, I believe. Yeah. Vlad, do you I think it is time. Do you agree?
Yes, it's some sort of measure of time. I don't know if it's actually the amount of robot steps or not, but it's definitely like, if it was the amount of robot steps or time, I mean, they're correlated, right? So yeah. It's one of those.
Yeah, I don't think they specifically mentioned in the paper what steps was defined as. Yeah, we can go to the next slide. Yeah, so here's the experiment that they ran with the human joystick control as opposed to the hand-coded example policy. And what's interesting is that there's a much steeper, I guess, learning curve in phase 1 as opposed to before. And this is kind of, I think, probably due to the fact that, I mean, it's less random exploration, like there's actually a human trying to get to the goal. But I should mention that there was no, they didn't make any effort to actually get good human examples, which is interesting because, and you can see that by, the average example of performance versus the best example versus the optimal example. And I mentioned on the previous slide, this optimal example was from the kind of one of the researchers doing their very best to solve the task. Whereas the best example and the average example were just, a bunch of random efforts to, try to get to the goal, but not take too much care in getting there optimally. And so the big difference between this plot and the one you saw before is this is from the agent learning from actual kind of human joystick control trajectories. And the authors claim that the reason why they sort of phase 1 and phase 2 result in sort of better performance is because there is a greater variety of training data generated in phase one. And so you get kind of better generalization. And then that means and also notice there's much less variance at the 95% confidence interval. So these dotted lines that you can see that's the 95 confidence interval across the 10 evaluation runs. Yeah, I think we can go to the next slide. Yeah, so here's the second task, which was obstacle avoidance. The state space now is the direction and distance to the goal state, and also the locations of the obstacles. Reward being 1 if the target point is reached, and -1 if it hits an object, and 0 otherwise. And for each of the runs, the robot is started in a random pose 3 meters away from the goal. And then, like in the previous example, the evaluation metric is again the number of time steps to reach the goal state. And for this one, there's no kind of hard-coded supplied control policy. All of the trajectories come from a human using a joystick to control the robot. Next slide. So here's a plot showing the successful runs, and note that during phase one, so again, out of 10, because that's the number of evaluation runs they perform. So you can see here during phase one, the robot's not really quite getting there. Basically they sort of say it's a harder environment because there are no walls to bound the agent. So the robot could sort of miss the target and have to spend time circling back. And I think they had a limit on how many time steps it could be done, and that's why some of these human joystick trajectories weren't successful, because I suppose they just missed the goal. And because there's no walls, they sort of say, it basically means that some of these policies could miss the goal state and not be able to recover. But the other thing to note here is after 10 phase 2 training runs, once the robot has learned to find the goal state from one of the starting positions, it can solve it from all of the other ones. And that happens at about phase 2 or after 10 phase 2 runs. Next slide. So this is again showing the number of steps it took to reach the goal, and you can see that the performance improvement in phase 1 is much more dramatic than it is in phase 2. And also the other thing to note is that the total time to achieve optimal performance was about 2 hours. So I guess, Laura, to answer your question a little bit in terms of like this total time, like I guess 30 phase 1 training runs plus 30 phase 2 training runs, that whole process took 2 hours. Next slide. The other thing to note is that they wanted to kind of they also ran a simulation for the obstacle, for actually both tasks. They ran a simulation of the robot to kind of see how much phase 1, like how the different, actually for the collision following tasks, they used a simulation to change that alpha term in front of the supplied control policy to see how much that made a difference. But I didn't show that result here. But yeah, this one is just demonstrating the fact that as you vary the starting distance, how many percentage of the time, how often without human support is the robot successful at avoiding the obstacles. And what you can see is that even at 1 meter, not only does it take 2 hours, but it only reaches the object less than half the time. And then at 3 meters, which was the setup in the actual task that they did experimentally, 3 meters away with no human support, not only did it take almost 7 hours of learning time, but it only reached the goal 20% of the time. And so this plot or this table was just the authors put to demonstrate the importance of having that phase one for training mobile robots, at least in 2002. Phase one is really important to be able to have the robot bootstrap off of human demonstrations. And then I think the next slide is conclusions, Vlad.
Yeah. Yeah, the thing, I guess to wrap all this up, the things to really note is that what they were trying to show in that last slide, and like what you were saying, is that phase one really does help with learning. Like essentially in the last slide was phase one had 0 episodes, right? And it was just all phase two. And they were showing that in that case, if it was just phase two learning where the agent's learning on its own, it would take significantly longer, like up to like close to 7 hours instead of like 2. So that, I guess that's the main conclusion, that like, okay, phase one, human demonstrations, using human experiences does improve the time it takes to learn something with these robots. And the other thing they really wanted to mention, which is like this third point here actually in the takeaways, but that we noticed that in phase two, the performance of the agent still keeps on improving. Maybe I can quickly go back. Like we can see that in phase two, it still gets lower and lower. So like, it's not that the agent is just learning how to behave as good as like a human, which is like the phase one examples, or even like this best example here. It's actually improving afterwards. So it's not just like copying the experiences, but it's just using that as like a way to get started and help it learn. And then it's actually improving. So that's also an important thing to note. And that the human demonstrations were also by no means optimal. And this was able to learn off that. And that once again, that this is, you can do this without fine tuning sensors and having a person program this. So that's all great. But I guess the concerns or some interesting things that we thought was, so first of all, they kind of say that human demonstrations are not optimal. And they're like, by no means were they amazing demonstrations. And they're like, they were just okay demonstrations. But they don't really quantify this in any way. They don't really mention like what that means, or how, like, we have no like metric to really judge that. And I guess one interesting thing is, how much does this human demonstration quality actually matter? So how good are the demonstrations? How good do they actually have to be? Because they kind of make this like very high level claim that they're obviously not perfect in their example, but how close to perfect do they have to be for this to even be like reasonably helpful? Is an interesting question. How many demonstrations are also needed? As you might recall from the slides, they kind of stuck to the same amount of episodes or demonstrations from a human to train each time. And they don't really mention like, what if we doubled it? How, like, would that be okay? What if we only use like 5 human episodes? Like how much fast, like how would the learning look like then? So how much do we actually need as human? And then finally, I guess that kind of brings up the final point, which is, how does this scale to the more complex tasks? Because we can imagine in more complex tasks, how much human demonstrations do you need and how good do they have to be? Because something that's like very challenging, you probably need way more. And how much do you actually need there? And how good do they have to be then? So that's kind of an unknown question. So yeah, that's the end of the presentation.
Awesome. Thanks, guys. Laura, do you want to ask your question that you had in Discord?
Oh, yeah, sure. I just may have missed it when you were speaking, but what did they define success as in their runs?
So I think they defined it when like it was the last, I don't remember the exact definition, maybe you remember, but it was something around the lines of like, if there is some, sorry, the last 5 episodes were within some like range of the current performance or something like that. So you can see there's like basically this like flat line of the number of steps they use. So it's like, there's no more improvement over these past steps. So we should just stop it there.
But did it matter whether they hit obstacles along the way, or was it deemed like automatically unsuccessful if they were to hit an obstacle along the trajectory?
That's a great question. I don't know. Theron, do you remember?
No, you could hit obstacles, I think, because you only got a reward of -1, and the I don't think the episode terminated. But yeah, I'd have to confirm that. But yeah, because their measure of success is reaching the optimal, as Vlad mentioned, within 95% confidence, you wouldn't be able to have it wouldn't, yeah. Even if you hit an obstacle, you wouldn't get optimal performance.
Interesting. That seems slightly odd to me, if what their goal of the experiment is obstacle avoidance, to not define unsuccess as hitting an obstacle, but maybe there's a reason for that.
Yeah, I mean, they could have actually mentioned that in the paper, as like the episode could have terminated after they hit an obstacle. I'd have to confirm that. It would make sense that that would be the case, but I don't remember reading that specifically.
Yeah, because otherwise, if it's just whether it reaches the goal or not, then they would have to maybe set a time limit on how long it would be able to take to reach that goal in order to like define success.
Yeah, sorry, I just rechecked in the paper, and they do say that an experimental run terminates when the robot either reaches the goal or hits an obstacle. So yes,
cool.
yeah.
Cool. Any other questions? All right, I'm going to take that as a no. So please drop at least one thing you liked and one thing that could have been improved, either about the presentation or the research, into chat. After Tuesday's class, I went through and read all the comments, and there was a bunch of good things, much more thorough than I could have given myself. So I really appreciate that you guys wrote the comments, took the time to do that, and it was all very constructive, which is great. I realized after the fact, ooh, I probably should have said something about please don't be a jerk, but you all did that automatically, not being jerks. So thank you. For the people who are presenting their papers next week, I recommend that the 3 groups coordinate so that they tell each other beforehand what order they're going in and how long they're planning on taking. Because if we only have 80 minutes, we need to figure out how that's going to shake out. And the final thing I'll mention is, let's see if I can do this. There we go. Whoops. There we go. So, Precision Martial Arts is in Corvallis, Oregon, and it is co-owned by Bill Smart. If you ever get a chance to meet Bill, he is awesome. And he was one of the authors on this last paper. I know he and another professor, when they meet up at conferences, they I believe they do jujitsu, yeah, and they have competitions. It's kind of cool to hear them talk about 2 well-respected professors beating each other up, or throwing each other. I guess they don't really strike. Anyway, complete aside, if you get a chance to meet Bill Smart, he's awesome. So with that, I think we'll wrap up a few minutes early. But again, if you have questions about the write-up that's due on Saturday, please just let me know. And otherwise, I'll see you on Tuesday with our final guest speaker. So thanks for the presentations again, and have a good weekend.